The blue periodic table, and flip it over and look at this chart. This is going to become your go-to thing.
You better find it, quick. I better find it.
Yeah.
I think I took one off the table the other day. Oh my gosh, I did. I'm so sorry. I don't know how you find anything. Just like in your back.
Okay.
But then you can't write stuff on it as you need
I
it.
always find it.
Yeah, it's not like I can use that stuff on the test anyway, so what's the matter?
I know.
Yeah, exactly.
Knowing
I hope
you
you know
know
that today in like when we were talking.
I'll do.
And
You actually
I
figured
was
it out.
like, like that. And right as I went like that, I made
Oh, no,
eye
the
contact
assignment.
like standing in the
Like what
window
just happened
front.
today.
Oh, good. And I went like,
Everyone's device.
and Fred's like, what happened? I was like, I just grabbed something. I went like
Good
this
enough.
at a dude.
Good enough.
That was a simple test.
That's funny. It was not. No, that is funny. He took it. That's funny. He took her running.
Okay. Kevin.
I did.
Okay, thank you. All right. So what you have, we are going to spend much time talking about this. This is called a standard reduction table. So listen to me very carefully. This is a reduction table. Every reaction that's on here, oddly enough, is a reduction reaction. Hence the term reduction table. Now, over here on the right-hand side, you have a series of numbers. That's measured in volts. So let me kind of begin to explain how this table works. These are E naught values. E naught, when you see anything with the naught on it, the zero, that just means it's under standard conditions. Standard conditions in reactions that involve aqueous things occur at 25 degrees Celsius. And all the solutions are 1 mole. So that's kind of standard conditions. But it's weird is that if you do gas law standard conditions, gas law standard conditions are at 0 degrees Celsius. So it's like you have this 25-degree swing between gas laws, which are set at 0, where water freezes, and then you have standard conditions at 25 degrees, which is ungodly warm, because like typical room temperatures are like 22 degrees. I can guarantee you if I warm this up to 25, it's like, oh, Burkett, oh, I feel flush, I feel hot, okay? So you go from doing this in a deep freeze to, sweating. So, but here's the point, when you see the E naught value, that just means under standard conditions, and that's true of a whole bunch of things we'll get into later. You have the letter V on the end of it, that stands for volts, okay? And later on, you'll see where this comes from. And for those of you that have taken chemistry, or excuse me, have physics, you'll have a better understanding of this. That technically has units of joules per coulomb, okay? Joules is a measure of energy, coulombs is a measure of charge, okay? Don't worry about it for now, just accept it. Basically, it's how much energy there is in the system, okay? That's the short version. The higher it is, the more energy there is. So how this works is that they established hydrogen as the baseline. And they said, we need to establish something as the reference. So this reaction where you take 2 hydronium ions and you take in 2 electrons and it forms hydrogen gas, that's defined as like a benchmark of 0. So like what you're going to be dealing with today in the lab, you're going to be dealing with copper. Now, here's what's important, and this is why it is so vital that you begin to look at the form that these species are in. So this is going to be Cu2+, it has the capacity to gain 2 electrons and form elemental copper. Okay, so notice that has a positive value of 0.34. So here's the general trend. The farther up you are on this chart, the bigger the positive values are, and the more likely it is to go in that direction. So if you come up here to the top and you have fluorine gas gaining 2 electrons, forming the fluoride ion, that has a value of 2.87. So what that means is that fluorine gas really wants to take in electrons and form fluoride ions. Okay, it really wants to go in that direction, which is why fluorine gas is highly poisonous, because of the fact that you breathe that in, it's going to search out electrons, and that's going to come from your lungs, which is bad. Okay, so this is why fluorine gas is so poisonous, because of the fact that it is so willing to take in electrons. Now, big picture. So do you think fluorine gas is a good oxidizing agent or a good reducing agent?
Good oxidizing agent.
Yes, because it's reduced. So fluorine gas is a great oxidizing agent because of the fact that it wants to take in electrons and turn into the fluoride ions. Okay? Now you come down here and you look at copper. Now here's the difference. This is copper ion, Cu2+. Wants to gain 2 electrons and form elemental copper. Notice that that value is 0.34. Okay? So relative, that's kind of up there a ways. So that what that means is that copper really becomes more stable. It wants to end up as copper. This is why we use copper in some roofing materials. Like some houses will have like copper on the outside. It's why we have copper pennies. Because of the fact that copper really likes to exist as elemental copper. It doesn't like to exist as the copper ions. Now, below that, you have Zn2 plus 2 electrons. This has a value of negative 0.76. So what that means is that zinc really doesn't like to take in electrons. Okay? What that means is the fact that this reaction, when you're down here with that negative 7.76, this really doesn't want to happen. So what that means is, in contrast to like the copper, zinc actually is more willing to exist as an ion and less as elemental zinc. If you go way down to the bottom, you have lithium plus an electron becoming elemental lithium, and that's negative 3.05. So what that means is that this is horrible, okay? Lithium is horrible at being an oxidizing agent, okay? It does not want to take in an electron, because lithium has that one little valence electron out there, and it really wants to look like helium, so it wants to give that electron away. This is why we don't build jewelry out of lithium, okay? Because lithium doesn't like to exist as lithium. Lithium wants to give away electrons, okay? If someone says, oh, here's the bracelet of lithium, don't wear it, okay? Because your skin has water on it. Where do you think it's going to react with? The water in your skin. This is bad, okay? If someone says, hey, let's go to Colorado, let's go panning for elemental lithium, okay? Don't go. You're not going to find it because it sucks as existing as elemental lithium. Now, in contrast to this, come up here and look at where gold is. Gold is AU. This is the easiest way to remember this. If someone steals your gold watch, you go, AU, come back with my gold watch. So, no, that's a true story. So, silver is AG. You go, ah, gee, someone stole my silver watch. So, you've never heard that? No. Seriously. You guys don't even wear watches anymore. All right. So, notice that gold is way up here at the top. Guess what? That's what makes gold so precious. Because it doesn't react with anything. Gold wants to exist as gold. Now, if you want to see the pattern, and if you can figure out the pattern of one thing, you can overlay that onto a couple of different ideas. So, a reaction that you all have done, and I've done for you, is that you take a strip of magnesium and you put that in hydrochloric acid. Okay, we're just going to do the net ionic, boom. You're going to get Mg2 plus and hydrogen gas. You all have seen this done countless times since you've been in Chem 1, okay? You've seen this happen. Now we're going to look at it in terms of this chart. So, this is the key. You have to understand what you are starting with. So if you come down here and you can find magnesium about a fourth of the way up. So you have Mg2 plus 2 electrons ending up with Mg, and that has a value of negative 2.37. So does this reaction want to go, this sounds biblical, but it doesn't want to go in the way that it is written. No, this does not want to go in the way that it is written. What does it want to do? It wants to get flipped over, okay? So magnesium ions don't want to take in electrons and form magnesium. Magnesium wants to give away electrons and turn into magnesium ions. Now, the other thing here is that you have hydronium ions. You do not have hydrogen gas. You have H plus potentially gaining 2 electrons and turning into H2, and that's 0. Now, there's a couple of ways, and this is going to be important. This is actually on the chart. It's actually above this. Because some people like to play, it's almost like a betting app. We're going to play the over-under game, okay? So if you're familiar with betting, you play the over-under. So here's the story. So you have H plus going like this, and then you have the magnesium ions going like this. So if the reaction is going to happen, and this does, notice that hydrogen is up above, this is the over-under game. Hydrogen ions is above the magnesium. Notice that you do not start, what are you pointing at?
Oh, nothing, I'm just holding this cup.
Oh, I thought you were pointing like I
No.
should see something.
No, I was literally just holding this cup and poking.
Okay, I literally thought, I was like, am I supposed to see something? Because right now I'm blind because I don't have my glasses on. So luckily I can see the cup. So, here's the story.
I'm just,
You do not have hydrogen gas. You do not have magnesium ions. What do you have? You have elemental magnesium and you have hydronium ions. Okay? So here's the question. Do the hydronium ions have enough oomph, pull, whatever you want to put it, machismo, to come up to the magnesium and go, hey, can I take away your electrons? That's the fundamental question. This is a tug of war.
Yes.
When you do the lab today, you view this through the prism of a tug of war.
yes.
So when this hydronium ion, which is just nothing but a single proton, there's nothing to it, literally, it is a single proton. It's like it doesn't even have a neutron to hang out with. It is a single proton. Okay? This is as simple as subatomic particle as you can get. It is a proton. Okay? One lonely proton. It's okay. It comes up to the elemental magnesium.
You're stronger than him.
And it says, hey, can I take away an electron? What does the magnesium do?
Absolutely.
Absolutely. It says, here, take them. They're annoying.
You
Okay?
look lonely,
So
weird.
those two,
I take care of
you know, Edwin and Eddie, the outside electrons, okay, they don't care about them. It's like, because I'm going to become more stable once I get rid of them. So in terms of the over-under game, and you remember this from the lab today, if this is hydronium ions, if hydronium ions, you put them in with the magnesium, if the hydronium ions are above the magnesium, the reaction is going to take place. Okay? Go with this. Now, if you'll notice, you have, way up here at the top, you have silver. Ag plus plus 1 electron. Now, if I take a piece of silver and put that into, there's no H there, into a solution of hydrochloric acid, what's going to happen?
Nothing.
Nothing, because it's the over-under game. Silver is above hydrogen. No reaction is going to take place. Okay? But again, you have elemental silver, not silver ions. Okay? So hydronium ions can't take away electrons from silver, but they can take away electrons from anything that's below that. Okay? Does that make sense? Now, for those of you that are math nerds, okay? Math nerds. We're going to get into something later called the standard reduction potential. So, if you look at this in terms of mathematically, you have 2H plus 2 electrons, hydrogen, that's 0. Then you have Mg2 plus 2 electrons ending in magnesium, and that's negative 2.37. So, here's the story. This reaction gets reversed. Okay, when this reaction takes place, this gets reversed. Magnesium turns into Mg2 plus. So if you have a negative standard reduction potential going in this direction, if you reverse it, what do you think happens to the sign of that reduction potential?
Positive.
It goes positive. Now check my math. If I take a positive 2.37, because now it's a positive, and add that to 0, do I get a positive number?
Yes.
Now, so those of you that are math nerds, if you add together the reduction potentials and you get a positive number, that means the reaction is spontaneous and it's going to take place. Okay? Whoa, come back. So, but if you look at what happens when you do that with silver, so with the silver, okay, you have Ag plus 1 electron, and that's 0.80. If you tried to reverse that, you would have negative 0.8 plus 0. You get a negative standard voltage potential, and it's a non-spontaneous reaction. Okay? So, I don't care how you view this. The over-under game, if you're a math nerd and you want to add numbers together, great. If you're a math nerd, if you add together the voltages and you get a positive number, it's a spontaneous reaction that's going to take place. If you add the numbers together and you get a negative value, it's not going to happen. If you're the over-under game, if the over is over, as the name implies, the under, the reaction is going to take place. If you have the over and then it's not going to take place. I don't care how you think through it, but come up with 1 or 2 reactions you can visualize like, okay, I know if I take magnesium and drop that in hydrochloric acid, I know I'm going to get a reaction. Use that as a model to apply that to other thought processes, okay? All right, so let's talk about the lab. So you're going to take a watch glass, which is like the big, kind of a huge contact lens, and you should have one in your drawer. And first thing you're going to do is you're going to take a couple of pieces of copper, okay? Boom, you got copper. This now, is that elemental copper, Cu, or is that Cu2 plus?
Cu.
Elemental copper, it's just copper, okay? So this is going to be important. So I'm starting with elemental copper. So if you look on your reduction chart, I'm not starting with copper ions. I'm starting with elemental copper, okay? I'm starting with elemental copper. So if a reaction takes place, I would have to end up in Cu2 plus. Now, to that, and I tell you, I'm going to have bottles in there. You're going to add zinc nitrate and lead nitrate to these. So you're going to have these on your watch glass. I'm also have what we call stereoscopes, which are kind of like the big kind of magnifying lenses, okay? And so you're going to put that underneath the stereoscope. You take a dropper and you're going to put a drop of zinc nitrate. Now, do you think you're going to worry about the nitrate?
No.
No, nitrate's just so it's soluble, okay? Do not worry about the nitrates. They're there. Don't worry about them. So I got Zn2 plus, and then I've got lead 2 plus. So here's what's going to happen. You're going to take Zn2 plus, and you're going to try and react that with copper, and you're going to see if something happens, okay? That's it. Then you do the same thing with lead,
Lead.
and you're gonna react that with copper. And then you're gonna see if something happens. So what you need to do, and this is why I tell you, wear safety glasses above all else. What I would do is you need to set up a chart, okay? So I would maybe have something like this where you have, here's the metal, you're gonna have three metals, metal or zinc and lead, okay? And then against that, you're gonna react it with copper ions, lead ions, and zinc ions, okay? Make that look much better than what I just randomly drew on a piece of paper. So do you think it's gonna do any good to react copper ions with copper?
No.
No, okay? I'm not gonna react zinc with zinc ions, and I'm not gonna react lead with lead ions. So you're gonna end up, if you count this, 1, 2, 3, 4, 5, 6, you're gonna have a potential of 6 reactions. Let me give you a hint. 3 of them you're going to see something happening, and 3 of them you're not, okay? And if it happens, it's going to happen. It's like, well, I kind of see tiny little bubbles. Maybe that's my reaction. No, okay? Tiny little bubbles is not a reaction.
Little bubble.
I'm just telling you. Sometimes that is a reaction. This is not it, okay? Now, some of these are going to be pretty cool, and this is why I had you look at these underneath the stereoscopes, because of the fact that stereoscopes are like kind of like very crude versions of microscopes. You use them to watch, to observe big things. And some of these are going to be pretty cool. Like you can see on these reactions take place, like you can see the crystals form, like, and especially that because it's magnified. So you can look at them and go, oh, you can actually see that reaction take place.
Yeah.
Especially if you can focus, like, put that drop of water on just like half of the piece of metal, and then when those reactions take place, you can see that transition line between the solution and the metal, and you can actually watch that reaction take place. So some of these are going to be pretty cool. Some are kind of like, okay, great, it happens, not a big deal. Okay, so that's going to be the first part of the lab. The second part, and these are 2 distinct things, so you don't have to do this in sequence. So I don't want everybody trying to do the copper and the metals all at once. We're going to kind of split this up. So you're going to take a pair of tweezers and the bottle of potassium permanganate, and you're going to grab with the tweezers just a few crystals of potassium permanganate. Okay, I mean just a few crystals. Okay. You're going to put, and be careful, especially with this potassium permanganate. Don't get it on your skin. Certainly don't get it in your eyes. It's going to be bad. Okay. And you're going to find the mass of those crystals. Okay, it's not going to be very much at all, and that's why I said, oh, what's the mass? Okay. You're going to dissolve that into 10.0 milliliters. This isn't, oh, it's about 10. This is exactly 10 milliliters. And got a beaker, put in the 10 milliliters, and you'll be amazed at how dark just a few crystals of potassium permanganate makes that solution. In another solution, I tell you to measure out 6 crystals of ferrous ammonium sulfate, and I've given you the molar mass of both of these. I've given you the molar mass. I say 6 crystals. You don't actually, because these are much bigger. Okay, the potassium permanganate crystals are very, 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 very small. The FeSO4 crystals are bigger, so you don't have to sit there and count. But I want more FeSO4 than I want MnO4. That's kind of the point of the story. So you kind of get those out, measured, find that mass. Then you're going to dissolve that in 5 milliliters of water. But then you're also going to add 12 drops of 1.5 molar sulfuric acid. What's the role of the sulfuric acid?
Provide
H plus.
That's giving you your H+. This is why this is done in an acidic environment. Then what's going to happen is that you're going to take that and you're going to mix these up drop by drop. So what you end up with is you're going to take MnO4 and you're gonna roll that all the way into Mn2 plus. So Mn2 plus solutions can do one of two things. They're either gonna be clear, or they're gonna have like a brownish tint to it, almost like muddy water. And because we're dealing with such small quantities, literally like this equilibrium can kind of go one way or the other. So don't flip out and go, oh my God, some of you might end up with clear solutions, some of you might end up with like kind of a brown, depending upon how much FeSO4 or how much Mn or KMnO4 that you add, okay? So don't flip out and go, mine looks different. It's because literally like one or two crystals of either one of these compounds is gonna alter where that equilibrium ends up, okay? So don't flip, oh my God, I did it wrong. Main point being is that you understand what the reaction is going to be. Then you've got 13 questions to answer. So, all right, kids, let's go do science. Kevin's locked out the camera.
Science.